Hello, this is Bruce. I'm going to go through something a little different today. You can see I've got a wall behind me. I'm going to use this as a screen. It's kind of like this is going to be sort of like a slideshow. I'm going to go through some images here. This is the first video that I've done that is really more of a teaching video than the other ones have been, because I want to give you an overview of this material. I mean, a real special one. Today with this, we're going to get back again to the heart of the difficulty with the existing story today. So I'm going to break this into segments, and I'm going to show you the first image, which is the path of physics. So what you see in this image represents the path of physics. Here we have the great minds of physics from Pythagoras and Democritus, Descartes, Newton, Einstein, Minkowski. And Minkowski is the one who developed space-time geometry from Einstein's work. And then Hubble, you see Hubble there. Hubble is the one who first discovered that the universe, the distant galaxies are all expanding from each other. And he didn't do that with the Hubble telescope, but the Hubble telescope was named after him because of that discovery. So this is the main path of physics that gives us our story today of what our universe is like. Now I want to take a look now at another path, and it is the one that is really the renewal path that this work follows. So up here you see the two books, Flatland, which was written in 1884, and Sphereland, which is in 1965. Sphereland was written after the discovery that our universe is expanding, and basically adapted the mathematics of Flatland to fit that. You also here see there Carl Sagan. If you want to know about Flatland just on a quick but pretty good level, watch Carl Sagan's YouTube video. If you can just search Carl Sagan YouTube Flatland, and you'll get it. So this is the other series. This is a science fiction series. And the difference is that this series imagined a flat universe where all the creatures are totally flat. And in the way it's all set up is people like us, three-dimensional creatures, are looking down on Flatland, and we think we see what they're missing. So in the stories, a person has a dream, and a creature from the higher dimensional universe comes down and reveals this higher dimensional nature that the Flatlanders can't see. And that nature is supposed to be that the Flatlanders can't see that there's an up-down dimension. So let me talk about that some. Now here you see an image from an article, and it's referenced there, A Guide to Flatland, What's It Like to Live in Two Dimensions. You see that picture there. And so what you have is a flat plane, and the idea is these higher dimensional creatures they're three-dimensional, and they can move through that flat plane, through the up-down dimension that the Flatlanders don't have. There you see the idea that there must be an up and down dimension that the Flatlanders are missing. Now Sphereland, which you see here, you see a ball as a sphere. And if you see that same image from the Flatland with a little plane and a balloon going through it, a three-dimensional thing going through it, the same idea applies in the surface of Sphereland. And so that just took the same idea. You're missing an up-down dimension, and just mapped it onto the surface of the sphere. But it's basically the same idea. And so now, without an image, let me just say that controversy swirled for since the 1800s. Was the two competing ideas. One is the path of physics that's ended up with space-time, and the path of science fiction that followed the Flatland Sphereland idea. The difference between those two, of course, is that physics understands time to be the fourth dimension, Whereas in Flatland, Sphereland, the idea was there must be a different dimension that's like space, so one that is like what we see in Flatland and Sphereland, a spatial dimension that we can't see or know. So in that, people could imagine beings of a higher dimension, that our universe might be like that. And mathematically, it was feasible that our universe could be like Sphereland. It could have been the surface of a higher dimensional, four-dimensional ball, basically. So you have those two competing scenarios. One is physics with its rigorous work, and the other is science fiction that actually worked on rigorous mathematics, but it wasn't experimental in nature. Now let's look at what happened. Something big happened. What happened was the COBE Background Explorer, which you see a picture of it here. That is a satellite that was put up that is surveying the distant background patterns in our universe. And that gives them a lot of information about large distances and what light does over large distances and the expansion that's happened in our universe. Now, the reason that's important is it put an end, apparent dead end, to the Flatland, Sphereland idea. And here you see that depicted. There's just a dead end, because here's the deal. If you had something like Sphereland, then light is traveling on the surface, then light would have to travel a curved path over very long distances, not over short ones. In Sphereland, it's pretty much flat over short distances, but over long distances, it's curved. And so light in a Sphereland kind of universe would follow a curved path over cosmic distances. And the Nobel Prize, there was a Nobel Prize project. It was awarded in 2006 to Mather and Smoot, their team, who discovered by looking at the COBE, Cosmic Background Explorer data, they proved really without a doubt that over cosmic distances, away from material, away from other matter, light goes in a straight line. It doesn't follow a curve. And they did that by measuring triangles in a special way. So that seems like then that the only thing in town is the space-time story of physics. But there is a little twist to the story. So here you see that same sphere of Sphereland. But it's pretty obvious when you look at it, wait, there's an inside there. That's an inside. And so a Flatlander, there's nothing that says he couldn't experience an inside like we do. We have an inner conscious behavior going on with us. And so the Flatlander who comes to tell us, wait, you've been thinking that we're missing a up-down dimension. No, but the thing is that you're missing an inner dimension. So, and an inner dimension, there is mathematics that tells about it, and it is rigorous. So that's where this story takes that direction. That extends, that revives, it renews the Flatland, Sphereland sequence or series. And so now we come to the final image, this is what I wanted to really tell you, is this is the nature of toy physics and of relation space, because the mathematics is called relation space. The story is called toy physics because it is a toy universe. It's a universe made of very simple but rigorous conceptual atoms. So here you see the Flatland, Sphereland now has a continuation. It isn't a dead end. The toy physics really could be called deep land, because instead of thinking that there's there's a fourth pointing dimension, a fourth dimension that points, no, there's a fourth dimension, but it doesn't point. It's an inner dimension. And it's mathematically, actually a really elegant mathematical concept that does use the same basic mathematical machinery that physics uses. Cartesian coordinates is Pythagorean in nature, and it it has the same kind of energy equations and so forth. So that's pretty much a summary of an overview of what's different about this and of what is going on with physics and with the Flatland Sphereland series. Both of them are missing the idea of an inner dimension. So thank you. I hope this was enjoyable to you. I hope this worked as far as the way I'm doing it. I would appreciate feedback. So subscribe to this channel. Get in touch with me if you can at bruce@storyweave.com. Thank you.